Welcome! In this session, we'll explore the LeetCode problem number 1441 titled Build an Array with Stack Operations. We'll take a deep dive into the problem requirements, discuss approaches to solve it, and ensure you understand the nuances of this simulation-based challenge. Let's get started. The problem requires us to build a target array using stack operations. The target array is a list of distinct integers sorted in strictly increasing order, and we are also given an integer n that defines the range, 1 and n, within which the stack operations must be performed. The stack starts empty, and we can use two operations, push, x, to add an integer x onto the stack, and pop, to remove the top element from the stack. The key constraint is that numbers must be pushed onto the stack in increasing order from 1 to n. If a number is pushed onto the stack but is not part of the target array, it must be immediately popped off. Our task is to determine a sequence of these operations that will build the target array and return it as a list of strings. To make this clearer, let's look at the first example. Here, the input target array is 1, 3, and n is 3. To build the target, we start by pushing 1 onto the stack. Next, we push 2, but since 2 is not in the target array, we immediately pop it off. Finally, we push 3 onto the stack. The stack now contains 1, 3, which matches the target array. The sequence of operations is push, push, pop, push. This ensures the target array is constructed in the correct order while adhering to the rules of the stack operations. In the second example, the target array is 1, 2, 3, and n is 3. Here, we simply push 1, then 2, and finally 3 onto the stack. Since all the numbers in the range, 1, n, are part of the target array, no pop operations are required. The stack ends up containing 1, 2, 3, which matches the target array perfectly. The resulting sequence of operations is push, push, push. This demonstrates how, when the target array includes all numbers in the range, we only need to perform push operations. In the third example, the target array is 1, 2, and n is 4. We push 1 onto the stack, then 2, which gives us a stack of 1, 2. The values 3 and 4 are not part of the target array, so we do not push them onto the stack or perform any additional operations. The sequence of operations for this case is simply push, push. This shows that when the target array contains fewer numbers than the range, 1 and n, we can ignore the extra values as long as we maintain the correct order in the stack. Finally, let's consider some edge cases. For example, if the target array is 1, and n is 1, we only need to push 1 onto the stack, resulting in push. If n is much larger, such as 100, we still only push 1 and ignore the rest of the numbers. On the other hand, if the target array is sparse, like 1, 50, with n equals 100, we would push numbers 1 through 50, popping all except 1 and 50. This ensures the stack matches the target while adhering to the range and order constraints. These examples highlight how the solution must adapt to the specific structure of the target array and the range of numbers provided. To solve the problem build an array with stack operations, we need to simulate the process of constructing the target array using a series of stack operations. The operations available are push, which adds the next integer to the stack, and pop, which removes the top integer from the stack. The goal is to determine the precise sequence of these operations to construct the target array without exceeding the range of numbers from 1 to n. One approach we can consider is a brute force method where we simulate the stack building process for all numbers from 1 to n. For each number, we check if it exists in the target array. If it does, we add a push operation. If it doesn't, we add both push and pop to simulate skipping over that number. This method ensures we account for every number in the range while building the desired output. In this brute force approach, the steps are straightforward. First, we loop through all numbers from 1 to n while keeping track of our position in the target array. For each number, if it matches the current element in the target array, we perform a push operation and move to the next element in target. Otherwise, we perform both push and pop to skip over the number. The process stops once we've processed all the elements in the target array. While this approach is simple to understand and implement, it has some trade-offs. The time complexity is O(n), as we iterate through all numbers from 1 to n, and the space complexity is also O(n), as we store the operations. However, this method is not efficient in cases where n is significantly larger than the maximum value in target, as we end up processing unnecessary numbers. To improve efficiency, we can use an optimized approach by terminating the loop early. Instead of iterating through all numbers from 1 to n, we only loop up to the maximum value in the target array. This eliminates unnecessary processing of numbers beyond what is needed. The steps are similar. We use a pointer to track our position in the target array, and for each number in the range up to max target, we check if it matches the current target element. If it does, we perform a push and move to the next element in target. Otherwise, we perform both push and pop to skip the number. This approach significantly reduces the time complexity to O, max, target, and the space complexity to O, max, target, making it more efficient. The key trade-off here is that the logic becomes slightly more complex since we need to ensure the loop terminates correctly once all elements in target are processed. Nonetheless, this method avoids redundant iterations and is particularly useful when n is much larger than max, target. Here is the Python implementation of the optimized approach. In this solution, we initialize an empty list called operations to store the sequence of stack operations, and a variable current to keep track of the current number we're processing. For each number in the target array, we check if current is less than the target number. If it is, we append push and pop operations to skip over the numbers until current matches the target. Once they are equal, we append a push to add the number to the stack and increment current. The process continues until all elements in the target array are processed. This implementation is efficient because it only iterates up to max, target, and simulates the stack operations needed to construct the target array with minimal computations. The result is a clean and scalable solution to the problem. In this problem, we aim to construct an array, target, using a stack with two operations, push to add the next integer to the stack, and pop to remove the most recently added integer. We're given an integer n, which represents the range of numbers from 1 to n available to use, and our goal is to determine the sequence of stack operations needed to build target. The algorithm starts with an empty list, operations, to store the sequence of stack commands. We also initialize a variable current to 1, which represents the number we're currently processing. The next step involves iterating through each value in the target array to simulate pushing the necessary numbers onto the stack. Let's look at how this is done in detail. As we go through each number in the target array, we may encounter numbers between current and the target value that are not part of the array. For such numbers, we perform both a push and an immediate pop. This means we push the number onto the stack to maintain the sequence but immediately remove it since it's not needed. After each push and pop, we increment current to move to the next number. When current matches the target number, we perform a single push operation to add it to the stack and increment current again. By following this process for each number in target, we build the correct sequence of operations. Once all numbers are processed, the operations list will contain the final sequence that constructs the target array. One key insight is that we don't need to explicitly maintain the stack itself. Instead, the combination of push and pop operations effectively simulates the stack's behavior. This approach avoids unnecessary memory usage while ensuring the correct sequence is followed. The algorithm also efficiently handles numbers that are skipped in target. For instance, numbers within the range 1 n that don't appear in target are quickly processed with a push followed by a pop. This design allows us to process each number from the target array in one pass, resulting in a time complexity of O, n, where n is the size of the target array. The space complexity is minimal, as we only maintain an operations list to store the sequence and a single variable, current, to track the next number to process. Now, let's consider some edge cases. If the target array is empty, no operations are needed, so the output is simply an empty list. If target contains just one number, the output will only include a push for that number. For a target array like 1, 2, n, where all numbers in the range are included, only push operations are needed for each number. On the other hand, for a target array with large gaps, such as 2, 4, the algorithm efficiently handles the skipped numbers by performing push and pop operations for numbers like 1 and 3 that are not in target. Let's walk through an example to see how this works in practice. Imagine the input is target equals 2, 4, and n equals 4. We start with current equals 1 and an empty operations list. First, we process the number 2. We push 1 and immediately pop it since 1 is not in target. Then, we push 2 and increment current to 3. Next, we process the number 4. We push 3 and immediately pop it for the same reason as before, then push 4 and increment current to 5. The final operations list is push, poppy push, push, poppy push. The time complexity of this approach is O(n), as we process each number in target and handle skipped numbers in constant time. The space complexity is O(1), as we only use the operations list for output. This sequence of operations efficiently builds the target array while simulating the stack behavior. This Python implementation solves the LeetCode problem number 1441. Build an array with stack operations. The goal is to simulate stack operations to construct the target array using numbers from 1 to n. Let's break the solution down step by step. 1. Initialization. The function buildArray is defined with two parameters, target, the target array to build, and n, the maximum number in the range, 1 and n, available for use. The list operations is initialized as an empty list to store the sequence of operations performed, and current is set to 1 to track the next number to consider. 2. Iterating through the target array. A for loop iterates over each number in the target array. The goal in each iteration is to simulate the process of pushing numbers into the stack until the number is reached. 3. Handling numbers not in the target array, inside the loop, while loop runs as long as current is less than number. For each iteration, the push operation adds the current number to the stack, and the pop operation removes it immediately since current is not part of the target array. After each pair of push and pop, current is increment. For adding the target number, once the while loop exits, current matches number. The push operation is appended to the operations list to add number to the stack. Afterward, current is increment to move to the next number. 5. Returning the result. After processing all numbers in target, the function returns the operations list, which contains the sequence of operations required to build the target array. ####key points. The while loop ensures that numbers not in the target array are handled correctly by performing both push and pop operations. The push operation is performed for each number in the target array to ensure it is added to the stack. The algorithm is efficient as it processes each number in the target array exactly once, making it linear in time complexity with respect to the size of the target array. This solution effectively handles all edge cases, such as when target contains only one element or when n is much larger than the largest number in target. By simulating the stack operations directly, it adheres to the problem constraints and produces the correct sequence of operations. This is the Java implementation of LeetCode problem number 1441, build an array with stack operations. The logic mirrors the Python implementation, using a list to store the sequence of stack operations. Key differences include explicit type declarations, e.g., list string, Java-specific collections like ArrayList, and the use of a for each loop for iterating over the target array. The algorithm efficiently constructs the desired sequence, ensuring all operations are correctly recorded. To begin solving this problem, let's look at the first example where the target array is 1, 3, and n is 3. We start by initializing an empty operations list and setting the current number to 1. The goal is to simulate the stack operations needed to build the target array. For the first target number, which is 1, the current value matches the target value. This means we can simply append push to the operations. After this, we increment current to 2. Now, moving to the second target number, which is 3, we notice that the current value, 2, is less than the target. To handle this, we append both push and pop to the operations to simulate pushing and immediately removing 2 from the stack. Then, we increment current to 3. At this point, the current value matches the target value, so we append another push to the operations. Finally, we increment current to 4, leaving us with the operations list as push, push, poppy push. With the operations list now complete, the final output for this example is push, push, poppy push. Moving on to the second example, the target array is 1, 2, 3, and n is again 3. Starting with an empty operations list and current set to 1, we begin processing the first target number, which is 1. Since the current value equals the target value, we append push to the operations and update current to 2. For the second target number, 2, the same logic applies, current matches the target, so we append push and then increment current to 3. At this point, the operations list stands at push, push. Now, for the third and final target number in this example, which is 3, the process is straightforward. The current value matches the target value, so we append push to the operations and update current to 4. At the end of this sequence, the operations list is push, push, push. This matches the target array exactly, so the final output is simply push, push, push. Now, let's look at another example where the target array is 2, 4, and n is 4. Again, we start with an empty operations list and set current to 1. In this example, the first target number is 2. Since the current value, 1, is less than the target, we append push and pop to the operations to simulate pushing and immediately removing 1 from the stack. Then, we increment current to 2. Now, the current value matches the target, so we append push to the operations and update current to 3. For the second target number, which is 4, the process is similar. While the current value, 3, is less than the target, we append push and pop to simulate pushing and removing 3. Then, we increment current to 4. At this point, the current value matches the target, so we append push to the operations and update current to 5. The operations list by now is push, poppy push, push, poppy push. The final output for this example is push, poppy push, push, popu push, which successfully builds the target array 2, 4. By following this step-by-step process, we ensure that all stack operations are correctly simulated to match the given target array for any input. This concludes the solution walkthrough for this problem. In this problem, the time complexity is determined by how we process the target array and generate the sequence of stack operations. First, we iterate through each element in target, which we'll call the outer loop. If the target array has m elements, this loop will run m times. Inside the outer loop, there's an inner while loop that runs whenever the current number being tracked is less than the next number in target. This inner loop essentially fills the gap by pushing and popping numbers until we reach the desired value. The number of iterations in this inner loop is equal to the difference between the largest number processed, max_target, and the total number of elements in target, m. Together, we have one push operation for each number in target, and the total iterations for the while loop amount to max_target m. Combining the contributions of both loops, the total time complexity can be calculated. The inner while loop accounts for O, max_target m, iterations, where max_target is the largest number in the target array. Meanwhile, the outer loop contributes O, m, iterations, one for each element in target. When we combine these two, the total time complexity simplifies to O, max_target. In the worst-case scenario, where the target array includes all numbers from 1 to n, max_target would equal n, and the time complexity reduces to O, n. This shows that the solution scales linearly with the size of the largest number in the target array. Now, let's analyze the space complexity. The main contributor here is the operations list, which stores the sequence of stack operations. For every number in target, we add one push operation to the list. Additionally, for numbers not in target, the inner while loop adds both a push and a pop operation for each iteration, resulting in 2 operations per skipped number. Altogether, the operations list contains m entries for the numbers in target and 2 max_target m entries for the skipped numbers, giving a total size of O, max_target. Besides this, the solution uses constant space for variables like current and number, meaning their contribution to space complexity is O, 1. Therefore, the total space complexity is dominated by the operations list, which is O, max_target. The total space complexity is determined by the size of the operations list, which is O, max_target. Comparing this solution to a naive approach, a brute force method might involve simulating a stack and performing push and pop operations in real time. While this would have the same asymptotic time and space complexity, it would introduce extra overhead for managing the stack structure. By directly constructing the operations list, this solution avoids that overhead, making it more efficient in practice. Furthermore, the solution is optimal for this problem, as it minimizes the number of operations by performing only the necessary pushes and pops. The time complexity of O, max_target, matches the theoretical lower bound for processing numbers up to max_target, and the space complexity is also optimal because the sequence of stack operations must be stored explicitly. Finally, let's examine the best, average, and worst-case scenarios. In the best case, the target array contains consecutive numbers from 1 to m, where m equals max_target. Here, no pop operations are needed, and both time and space complexity are O(m). In the average or worst case, the target array is sparse, meaning it includes fewer numbers but references values up to max_target. In this case, both the time and space complexity become O, max_target, due to the skipped numbers that require push and pop operations. Mathematically, the total number of iterations is bounded by max_target because every number from 1 to max_target is either pushed or processed with a push-pop pair. Since the operations list grows linearly with the number of operations performed, the space complexity is similarly O, max_target. When solving this problem, there are several common mistakes to watch out for. First, not accounting for skipped numbers is a frequent oversight. If a number is not in the target array, a corresponding pop operation must still be added to simulate removing it from the stack. Forgetting this violates the requirement to simulate the exact sequence of operations. Another issue is stopping the loop too early, such as halting once the target array is fully processed without considering all numbers up to the maximum value in the target. This leads to an incomplete simulation, as the operations for skipped numbers are also part of the sequence. Finally, hardcoding the range of numbers instead of dynamically deriving it from the target array is a mistake. Hardcoding makes the solution inflexible and prone to errors if the input changes, especially for edge cases or varying input sizes. Now, let's address a couple more pitfalls. Skipping edge cases is another common error. For instance, not handling an empty target array or cases where the array starts from 1 but skips intermediate numbers can lead to runtime errors or incorrect outputs. These scenarios need specific handling to ensure correctness. Additionally, overcomplicating the logic can cause unnecessary issues. Some solutions use extra data structures or complex loops to track operations, which can increase time complexity and make debugging harder. Keeping the implementation simple and focused on the problem requirements is critical for clarity and efficiency. To perform well in interviews, it's important to keep a few key insights in mind. First, understanding the constraints is crucial. The operations are limited to push and pop, and the goal is to simulate the target array exactly. Be sure to consider edge cases like an empty target or large input sizes. This problem is ultimately about recognizing patterns. It tests your ability to translate abstract constraints into a concrete implementation. From a performance perspective, aim for an O(n) solution, where n is the maximum value in the target array. Avoid solutions that involve multiple passes over the data, as they can be inefficient. Finally, communication is key. Clearly explain your approach by walking through the logic of when to use push and pop and how you ensure the sequence matches the target. Demonstrating this thought process is often just as important as the code itself. If you're looking to strengthen your understanding of stack-based problems, there are several related LeetCode problems worth exploring. Problem number 946, validate stack sequences, is closely related but focuses on checking if a given sequence of operations is valid rather than building one. Problem number 682, baseball game, involves using stacks to simulate calculations for game scores. Problem number 394, decode string, requires stack-based simulation to decode nested strings, which is another great example of stack usage. Lastly, problem number 155, min stack, introduces an additional constraint of retrieving the minimum value, which challenges your ability to manage stack operations efficiently. Studying these problems can deepen your understanding of stacks and how they're applied in different scenarios. Finally, let's discuss some alternative approaches to solving this problem. One efficient method is tracking the solution with a single loop. Here, you iterate through numbers from 1 to the maximum value in the target array, checking dynamically whether each number is part of the target. This approach is simple and runs in O(n), but it relies on careful handling of the simulation. Another option is pre-computing the operations. By comparing the target array with the range of numbers, you can generate a list of push and pop operations in advance. This can simplify processing but may require slightly more memory. Lastly, the two-pointer method involves using one pointer for the target array and another for the range of numbers. This approach is efficient for large inputs but can be a bit more complex to implement. Each method has its trade-offs, so choose one that best fits the problem constraints and your coding style. Great job! In conclusion, we tackled the problem by simulating stack operations to build the target array. We reviewed the algorithm, time, and space complexities while highlighting key concepts learned. Remember, simulation problems like this are great for improving logical thinking. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!